Okay, well, good morning, everyone. Firstly, thanks so much for coming. When I first discussed the possibility of running a reading group kind of on category theory, but tailored for people in statistics and probability, I had honestly no idea how much interest there would be, if any. And so it's amazing to see, well, as far as I can tell, 28 people here at the moment. Thank you so much for being here. So let's just dive right in, really. Okay, first, just some kind of housekeeping things. So I'm very grateful for the Prob AI Hub, who've given me a small discipline hopping award, which has made this reading group possible. And also particular thanks to Rob Cornish, Sam States, and Paolo Proni, who may or may not be in this meeting. They'll be giving presentations further down the line, so I'm extremely grateful for them giving up their time to present to us in a few weeks' time. Okay, so I guess you guys all read the abstract, so you're interested in kind of categorical probability and its potential applications for your own research. So this is not, of course, a course in category theory. There is no way in a couple of hours I could give you a full presentation of the beautiful maths that is category theory. And another reason is I'm myself not even a category theorist. As many or most of you will know, my own background is in computational statistics. And so I don't have any kind of formal research background in category theory. But hopefully for those of you who are similar to me, that is hopefully a reassuring thing, because for me, a few years ago, I knew zero category theory, and now I'm actively using it in my research. So I hope that's a kind of an encouraging thing. And so what is the purpose of these kind of reading group meetings? The aim is to hopefully showcase the usefulness of these categorical ideas for your research, hopefully in kind of the area of applied probability statistics, machine learning / AI. And I'm aware there are some people who actually are more from the actual categorical side attending this meeting. You're extremely welcome as well. And hopefully the way I'm presenting it and the kind of things we end up talking about will hopefully also give you ideas for potential research problems within categorical probability. So hopefully in some sense, there will be something for everyone. Although today's particular presentation, for those who already have background in categorical probability, you probably won't learn much new. So apologies for you folks for that. And and because I'm really targeting this for researchers within statistics, probability, machine learning, I'm not going to assume any prior knowledge of category theory, none whatsoever. But I am basically assuming you are comfortable with the traditional approach to doing probability and statistics through measure theory. And in fact, one of the ideal outcomes, from my perspective, is hopefully maybe through today and the other presentations this week, some of you will be interested to actually go away and learn some category theory yourself. And I've given just a couple of references here, which I personally found extremely useful. So the lecture notes of Paolo, I think are absolutely brilliant. I'm not sure if he's in this meeting, but yeah, I would highly, highly recommend his lecture notes. They are written up as a book, but you can also just download them from archive as well. And another resource, which again, personally, I found very useful, are a series of lectures just on YouTube by a guy, Bartosz Maluski. His lectures are not rigorous. He doesn't really go through the proofs, but he gives absolutely amazing intuition. And so for me personally, I kind of watched his videos and then read Paolo's notes kind of together. And I found that an extremely fun and fruitful way to learn category theory. Okay, so what are we doing? So the format should be roughly the same for the meeting. So the sessions, I've said 90 minutes, but of course, just if you need to go, just go whenever. And so this part, the first, 50 minutes up to an hour, will be the main presentation, which is recorded. So we're recording this, followed by up to 30 minutes of unrecorded, just general discussion or extended Q&A for whoever wants to stick around, essentially. And so there is a schedule. So today we're discussing kind of introduction to categorical probability, where I'll give some really basic results, if you like. And then next time, so in 2 weeks' time, I'll be presenting again. I'll be presenting Markov categories and their application to MCMC algorithms, in particular Metropolis Hastings. So we'll really see some of the payoff of the categorical thinking next time. And then for the rest of the kind of sessions, so we'll have Rob Cornish talking about stochastic symmetrization of neural networks, and then Sam Staten and Paolo Proni connecting categorical probability with some of their areas of expertise. So I'm extremely excited to see what Rob, Sam, and Paolo present later on. Okay, so when I tell people I'm interested in category theory, inevitably the first question, which is a perfectly good question, is, well, why? And so let me just on a very high level, explain what I see as some of the contributions of category theory for people in, let's say, probability, statistics, and machine learning. And on a very high level, I see category theory offering at least two things. So the first one is kind of the technical mathematical part. Category theory is, of course, a part of maths. It's a part of, pure maths, algebra, if you like. And so it has a whole range of technical tools, such as, definitions, the definition of a category, a functor, a monad, more specific constructions like Markov categories, and then tools like string diagrams. For most of you, or many of you, those words will mean nothing at this point, but these are kind of technical tools once you get your head around them that you can use for your problems in your own research. So there are kind of technical tools category theory offers. But then the other part is a much more kind of higher level contribution, if you like, which is a kind of a different perspective on the kind of research you're doing, which I've kind of just called a compositional way of thinking. And it's kind of hard to describe this at this point, but hopefully you'll kind of pick it up as we go along. And I would argue that this compositional way of thinking is much more suitable for the kind of highly compositional complex systems that we often have to reason with for our modern, data science, statistics, machine learning type problems. And so I hope that both of these will be useful for your research. So in terms of the first one, technical mathematical tools, here's a kind of slightly provocative example. So I'm sure you'll all recognize these two figures. So on the left, we have a kind of, a two-layer neural network with one hidden layer. And on the right, we have the very famous transformer architecture of Vaswani et al. Well, actually, I would say that these are both examples of string diagrams. So if you recognize, or you've even drawn these pictures yourself, you've been doing category theory without knowing it. And to give you a kind of teaser for next time, in 2 weeks' time, this will mean nothing to most of you, but this on the slide is actually a result I derived with Rob Cornish, which is a proof of reversibility of Metropolis Hastings purely through string diagrams. So of course, for most of you, this will mean absolutely nothing. But if you come back in 2 weeks' time, I will walk you through how this actually proves a reversibility of generalized forms of Metropolis Hastings. So that's a thing. Okay, and what about the second one? Let me just give a few more remarks in terms of the shift in perspective. All the kind of introductions to category theory I kind of saw all have some brief philosophical remarks. So here is my attempt to do that. And so I mentioned previously that thinking categorically gives you this different perspective on our kind of the problems that we're working on. And I want to argue that that shift in perspective is actually similar to other shifts in perspective that have happened in other fields, such as philosophy and even physics. I'm certainly not an expert, but you can later search for relational quantum mechanics. And just to give a very low resolution cartoon, in some kind of traditional views of philosophy/physics, people would argue that things just kind of exist independently of everything else. We've got the very famous dictum of Descartes, cogito ergo sum, I think, therefore I am. I'm sure it's an oversimplification, but he's saying kind of he just exists as a person independent of anything else. And within mathematics, if you take the kind of traditional set theoretic view, the thing people care about are sets, and their internal structure is inherently of interest. Within probability, if you take the traditional approach based on measure theory, the foundations are, well, things like sigma algebras, measures themselves. Those are the kind of the foundational objects on top of which we lay, distributions and so on. And Tobias Fritz had argued that this approach is like a low-level machine code-like approach, and it's kind of bottom-up / analytic. And if you go to the second column, there's this kind of shift in various branches, such as philosophy and physics, where people are kind of recognizing the importance of perspective of reference frame. So the most intuitive example might be something like velocity. In Newtonian dynamics, a particle just has a velocity v, and that's fine. Whereas if you think, say, in special relativity, of course, velocity isn't an intrinsic property. It entirely depends on your frame of reference. And so it's this shift in perspective where actually as the observer, your frame is extremely important. And we've got contemporary writers saying things like relations precede relata. So relationships are in some sense primary. The objects which are related are actually secondary in some sense. And I'll say no more because I'm not an expert. And then if we go to kind of the categorical view of kind of sets, instead of looking at sets themselves and their internal structure, the thing that really becomes of interest are the relationships between the sets. And there's a cornerstone result in category theory called the Yoneda lemma, which almost makes the quote of Ian McGilchrist rigorous in the sense that one of the corollaries of the Yoneda lemma is that in some sense, if you can tell me all of the relationships of an object, in some sense, I can tell you what that object is up to isomorphism. And then in terms of categorical probability, instead of starting with the individual objects, which are measurable spaces and sigma algebras and so on, the kind of foundational objects are actually distributions and kernels, which are the kind of transformations between the spaces. They become foundational. And I would argue that for people in probability and statistics, those are the things we work with on a day-to-day level. We don't interact with sigma algebras, so to speak. And so this provides, again, what Fritz would call a more high-level language that's top-down and synthetic. So yeah, hopefully that gives you some sense of what I mean by this shift in perspective. Okay, so having said that, that's my kind of fluffy general introduction. So I think for the majority of this session, I'm actually going to switch to a board on my iPad. So hopefully the technology will work. And this is a bit of an experiment for me as well. Okay, so I hope that is coming through. Okay, and feel free at any point to interrupt me if you have questions. We are being recorded, so bear that in mind, but I welcome any kind of comments or even corrections, because inevitably I'm sure I'll say some things that aren't quite right. Okay, so let's dive in then to some of the maths. So this reading group is on categorical probability, and so it seems that the right place to start is to discuss, well, what is a category? So let's just start with that. So let's say section 1 basics. Okay, so of course, categorical probability is based on category theory. And so we should start by talking about what is a category. So a category, I'll use the letter C. It's several things. So it's firstly a collection of objects. And I will denote objects with kind of curly capital letters, so X, Y, Z, etc. So it's a collection of objects and a collection of morphisms. And I'm using the word collection deliberately because it might be bigger than a set. A collection of morphisms, and I will use kind of little letters like F, and these morphisms go between objects. So every single morphism has a kind of source and a target, and I'll write that as F from X to Y. Okay, and what can we do with these such that? So firstly, we can compose morphisms. So if we have F as above and given also a G from Y to some object Z, we can form the composition. We can form the composition G after F, which goes from X and takes you straight to Z. I'll give some examples in a moment, but you can, for people in kind of stats and probability, you can certainly think of just functions and function composition at this point. And furthermore, so this composition has to be associative. So what do I mean by that? So if in addition we also have another morphism H that goes from, say, Z to W, we can form kind of the unambiguously form this triple composition. So if you do H after G after F, this is the same as if you did H after G after F. And so what that means is we can just unambiguously write H after G after F, and we don't have to bracket anything. And then thirdly, for all objects, we have identities. So for all objects X, there exists a kind of distinguished morphism that goes from X to X, which in some sense does nothing. So for example, if you do, so where F is going out of X, so if you do identity, no, F needs an X. So if you do F after identity on X, this is just F. And if you have a compatible morphism that goes into X and you do, say, F prime, this is just F prime. So whenever you compose the identity with something, the identity just does nothing. Okay, so that is the definition of a category. It's just an abstract mathematical object. And so let me immediately give you some examples. So examples. So the notation suggests that the first example should be sets and functions. And indeed, there is a category called set. So in set, the objects are all sets. So this is, as a kind of mathematical object, absolutely enormous, because every single set that you could think of is an object in this category. So for people who are more used to thinking about, topology and measurable spaces, this is way bigger than any individual, measurable space. Every single set you can think of is an object in this category. And what are the morphisms? So the morphisms, as the notation suggests, are just functions, between sets, using just the exact same notation. So X and Y sets, and F is just a function from X to Y. So then if you talk about composition, so G after F is just regular function composition. composition. And we all know function composition is associative, so this is associative. So I'll just put a tick. And then, of course, what is the identity? Well, the identity is just the identity function. So if you give me any set x, the mapping x goes to x is a well-defined function. So yeah, so the identity function is the identity morphism. In the sense that if you compose this with any other function, well, it doesn't do anything. Okay, so that's the first example. So yeah, the kind of collection of all sets and the mappings between them, the functions between them, are a category, as the kind of notation suggests. Okay, so let's give now a second example, which is in some sense on the opposite end of the spectrum. So when I gave you this definition of a category, if you have any background in algebra, for example, you know what a group is, hopefully alarm bells are ringing because, of course, for group theory, associativity and identity are two of the axioms that define a group. And so indeed, if you give me a group, there is a kind of canonical category which has the same structure. So and I'll write it maybe as G, kind of a group under addition. So let G plus be a group. And we can define a category now, which is often called the de-looping BG of G. So this is a category with a single object. So this is like the opposite end of the spectrum of set. So set had, where every single set was an object, whereas this category BG just has a single object that I'll just call star. Okay, and what about its morphism? So for every element of the group, this defines a morphism in this category. And I'm just going to use the same letter. We have a morphism in this category BG. And because there's only one object, the morphisms have to go from star to star. And what is composition then? So if you give me, two elements, so say H is also in G, if we want to then compose these elements in the category, so for example, we want to do H after G, by definition, this is just the group operation H plus G. So maybe the fact that I'm using the same letters is a bit confusing, but the idea is there is essentially a kind of bijection here. So every element of the group defines a morphism in this category, and composition in this category is the operation of the group. So I've written it as addition here, but it can be anything. So what about associativity? So associativity of this category just follows because of associativity of the group. So that's fine. What about identity? So there's only one object, so there's only one identity morphism, so identity star. So the identity morphism is just the identity of the group identity elements. And you can check because, of course, if you multiply the identity element with anything in the group, it doesn't do anything. And that exactly means it's also an identity morphism in the sense of category. So that actually verifies that this is in fact a category. Of course, groups have more structure because they also have inverses, but that wasn't necessary from the categorical perspective. And indeed, semi-groups or monoids, groups without inverses, are also categories. Okay, so that's just the second example, which is the opposite end of the spectrum. So you have this massive category set. On the other end of the spectrum, if you just have a category with a single object, that's a bit like a group. Okay, so now a third example, which will be for us in terms of categorical probability, the most important, and this is called measure. So measure is of course short for measurable or measure, and it's very similar to set. So in set, every single set was an object. In measure, the objects are going to be measurable spaces. So the objects are measurable spaces. So in other words, what I mean by that are sets equipped with a sigma algebra. Okay, so again, like set, this is huge because every single measurable space you can think of defines an object in this category. And what about the morphisms? So the morphisms are measurable functions between measurable spaces. And in my notation, I'll probably drop the sigma algebras and I'll just write f of x to y. But of course, both x and y are equipped with sigma algebras. So about composition. So composition is just function composition. So as in set. But we do have to have an extra remark. And this is well defined because the composition of measurable functions is itself a measurable function. So this is well defined. Associativity is Also true, just same as in set, because function composition is associative. That's fine. And what about identity? So the identities are the same as in set. So so if you give me a space, a measurable space X, it is also the mapping X to X. And again, we have to remark, so the identity is always measurable for any sigma algebra on X. You know, if you just look at the definition of measurability, it is basically a tautology at this point. It's saying that a set A is measurable if the set A is measurable. So yes. So the identity functions are also the identity morphisms in Mej, and they're measurable, so they are in this category. Okay, we will certainly come back to, yes, this this category very shortly, because this is going to be the foundation of what comes for the rest of this presentation. Okay, so I've given you the definition of a category. I've given you 3 examples: set, kind of delooping of a group, and Mej. And as is typical in maths, when you define some abstract kind of object, like a group, for example, or a vector space, that's fine, but things get really interesting once you define transformations that preserve the structure of those objects. So for example, in linear algebra, things get really interesting once you start talking about linear transformations between vector spaces. In group theory, things get really interesting once you start talking about homomorphisms. And the same is true in category theory, because we can talk about functors, which are transformations between categories that preserve the structure. So I'll first give you the abstract definition, and then I'll give you a really important example for categorical probability. So what is the definition of a functor? So a functor, now I use the letter capital F, is a transformation between 2 categories. So C and D are 2 categories, and a functor is a transformation between them. And so what is it? So a functor is several things. So for all objects X of C, a functor is basically a mapping that maps these objects into D. So F of X is an object in D. So you can think of it a bit like a function if you like, but of course these categories can be much bigger. So it's a mapping that takes objects in C and maps them to objects in D. So that's the first part. And the second part is their action on morphisms. And we actually use the same notation, but in general, there isn't a clash. So if we take any morphism X to Y in C, we use the same notation. So we write F of F as well. So F of F is a morphism in D that goes from F of X to F of Y. Because remember, F went from X to Y in C. So F of X is an element in D. F of Y is an element in D. And then F of F is a morphism between those 2 objects, is a morphism in D. And then, as I said before, the thing that makes it interesting is the fact that it preserves the categorical structure. So such that if you do a composition in C, so for example, you do G after F, this is a composition in C, and you apply the functor to this morphism, it's the same as if you did the corresponding composition, but in D. So if you did the functor to the individual morphisms and then compose them in D, that's the same as first composing them in C and transforming that composition. And also the functor has to preserve the identities. So if you do F of X to an identity, this has to give you the identity in D, but on F of X instead. So this is the abstract definition of a functor. The intuition is it's a transformation between categories that preserves the categorical structure. And so it transforms both the objects and the morphisms. Okay, so now let's give kind of the prime example, which is an absolute foundation within categorical probability, and this is going to be the Geary functor. And I believe this goes back to a paper of Geary from the 1980s. Okay, so in the definition of a functor, we said it went between 2 categories C and D, but there's no reason why they can't be the same category. So a functor could map one category, into itself. And that's what this Geary functor is going to do. And I'm going to use the letter curly P. It's a functor from Mej to Mej. So remember, what is Mej? Mej is this category where the objects are measurable spaces and the morphisms are measurable functions between them. And the composition is just, function composition, but of measurable functions. And we're now defining a functor on Mej. And so from this definition, we have to define 2 things: the action on objects, then the action on morphisms, and then we have to check that the 2 functor axioms are that they hold. So let's first talk about objects. So give me a measurable space. So given a measurable space x sigma x, we define f, and I'll just write p of x to save me writing. So p of x is the action of the Geary functor on this measurable space. And what it sends x to is it sends it to the set of probability measures on x. So I'll just let that sink in for a moment. So you give me any measurable space x, and what p does to x is it sends that space to the set of all probability measures defined on x. Because remember, we've also specified a sigma algebra for x, so we already know, what the events are, if you like. And p of x is the set of all probability measures on that space x. And there's one more thing I have to say, because of course this has to be an object in Mesh, and so furthermore we have to equip this set with a sigma algebra. So this is equipped with the following sigma algebra. So it's the sigma algebra generated by, and it's generated essentially by these evaluation maps that evaluate a given probability measure at a set A. So for any measurable set A, this defines a mapping on P of X, and we then pick the smallest sigma algebra that makes all of these mappings measurable. This is important actually, but it's also kind of a technicality. So if this doesn't mean much to you, I wouldn't worry about it. You just need to remember that P of X has to be a measurable space, and so it's not enough just to say it's the set of probability measures. We have to also equip it with a sigma algebra, and we will see that this is a canonical kind of choice, and it will lead to many nice things further down the line, which we'll see in a moment. Okay, so that's the first part. That's the action on objects. What about morphisms? So remember, the morphisms in Mesh are measurable functions. So let f from x to y, so x and y are two measurable spaces, and let this f be a measurable function. So what we have to define then is p of f, and we already know its signature because we've defined p on objects, so it has to go from p of x to p of y. So in other words, p of f is a mapping that takes as input a probability measure on x, and it spits out a probability measure on y. And what we have at our disposal is a measurable function that takes you from x to y. And so if you just step back for a moment and think about it, there is a kind of canonical choice for p of f. So remember, we have two things at our disposal. We have a function, a measurable function that goes from x to y, and we have a probability measure on x, and we need to somehow obtain a probability measure on y. And so the canonical thing to do is just to take, well, if you give me this mu, is to map it to the push forward measure, which I'll write as mu hash of f. And if you're unfamiliar with push forward, so what is the definition? So if you give me any measurable set in y, so b is measurable in y, by definition, this is the measure when you take the inverse image of the set b, and it's the mass of that set in x under mu. So this is the action of the functor on morphisms. So you give me f, and now it's a mapping from p of x to p of y that sends any probability measure on x to its push forward under f, which is a measure on y. Okay, and so the things we have to check, and looking at the time, I'm not sure if I will spell this out, but we need to check, for example, that if you do p of g after f, that this is equal to p of g composed with p of f. And this is true, so maybe I won't spell that out, I'll leave that as an exercise. Essentially, it's because if you push forward a composition, it's the same as doing the push forward of the push forward. If you just write it down, you'll see it is just the definition pretty much. And then we also have to check that we preserve identities. So if you consider the push forward of an identity mapping, so the push forward of identity mapping, so if you give me a measure and you don't do anything to the point, well, of course, you haven't done anything to the measure either. So this is exactly also the identity on measures. So this does actually define a functor. And so again, it's worth stepping back for a moment, because again, if you're more familiar with things like measure theory and topology, you're used to thinking about kind of measurable mappings or continuous mappings. Well, this is way bigger in some sense. because this functor is doing something on every single measurable space and on every single measurable function. So it's really big in some sense, and yet despite being so big, it actually preserves the structure of mesh. Because what we've shown that if you take compositions in terms of just purely composing measurable functions, that's kind of, and then consider their push forwards on measures, that composition is preserved. So this, yeah, I think is really cool and really quite remarkable. Okay, so that's the first example of a functor. It's a highly non-trivial functor, but in fact, it's actually much more than just a functor. It is, in fact, a monad. So I'm not going to give, I think, the strict definition of a monad, because that would take me too long. And I'd have to define natural transformations, which I think at this point is not worth doing. So let me just talk through what that means, and we'll do some maths. So this functor P, it acts mesh to mesh. So if you give me a measurable space, it acts on it and gives you another measurable space. So because it's mapping a category into itself, there's no reason why you couldn't compose the functor with itself. In other words, there's no reason at all why we couldn't consider, for example, P of X, right? Because the whole point was P of X is a measurable space. That's why we took great pains to define a sigma algebra on P of X. So P of X is itself a measurable space. So why not apply P to P of X? And what does that give us? Well, it gives us the collection of alphas, which are probability measures on P of X. So these are probability measures on X. So it's the collection of probability measures on probability measures on X. Okay, so that's a thing. I mean, if you're familiar with kind of random measures, that's nothing too scary. It is a thing. But then I just said that this scary functor is actually a monad. And part of what being a monad means is if you give me such an object, such an element, say alpha, in P of X, we have to be able to canonically map it down to something in P of X. So there's a sense in which we can kind of simplify down these kind of generalized elements to just generalized elements. So how would we do that? So if you just give me some measurable set in A, so we're considering measures on this set X. So consider the following. So remember, alpha is a measure on measures. So if you like, it defines a random measure. And so if you like, what we could do is we could sample from alpha. Alpha gives us a law on probability measures. So let's sample a random measure mu from alpha and then take the expectation. So we could take the expectation, say, of mu of A, because we've got some measurable sets. So mu is drawn from alpha, and it's the kind of expected mass of this set A. So if you want to write that out explicitly, you can write it in terms of integral notation. So this would be an integral with respect to alpha, where mu is kind of the element, and mu is a measure, mu of A, and this is over P of X. What I want to basically say is that the mapping from A to this is a probability measure. And I'm not going to prove that, but yeah, it's true. So in other words, what we've done is we've defined a mapping mx. So typically people would use mu, but I'm using mu for measures, so I'm going to use m. That goes from P of X, and it maps you into P of X. So, you gave me this alpha, and I mapped it to this thing here above. This mapping A maps to this expression. And this is a probability measure on X. And in fact, this mx is actually a kind of canonical construction, because in this argument that I used, we just kind of integrated over with respect to alpha, but we didn't use any specific properties of the underlying space X. And so because we could define this canonically for every single X, this is what is known as a natural transformation, which I won't actually spell out, but it's just intuitively, it's a canonical construction for every single measurable space X. Okay, so that's part of what it means to be a monad. And at this point, I'm just going to immediately use this because it turns out whenever you have a monad, you can actually define a new category. So, and this is called the Kleisli category. And so this is arguably the first step, or at least for me, it was a point where in terms of category theory, you really have to now kind of expand your mind and go to a higher level, if you like. So what have we said so far? So we defined this category measurable spaces and measurable functions. We defined this functor that acts on mesh. And we saw that, well, we partially saw that it's a monad in the sense that if you give a measure on measures, I can kind of collapse that down to just a measure. And so we're going to define a new category known as the Kleisli category of this monad. And you can do this for any monad, but we'll just do it for this particular monad, the Geary monad. And so we're going to define a new category. And at the end, you'll see that it's actually something we know and love. Okay, so we're defining a new category. So if we go back to the definition of a category, we have to define a bunch of things. We have to define the objects, the morphisms. We have to define composition between the morphisms. We have to check the identity morphisms. And then we have to check that the composition is associative. So firstly, then, we have to define the objects. So what are the objects? So P goes from mesh to mesh. And in fact, the objects of the Kleisli category are the same as mesh, So in other words, these are just measurable spaces. So far, so good. So the Kleisli category has exactly the same objects as the underlying category. So in this case, mesh. What about the morphisms? So this is where things get interesting and we have to expand our mind a bit. So by definition, if you like, so a morphism in the Kleisli category, I'm going to use kind of just a capital P, not a curly P. And I'm going to use a different arrow in terms of notation to define morphisms in the Kleisli category. So P goes from X to Y in the Kleisli category, essentially if and only if P is a morphism in mesh, which goes from X to P of Y. So this is the bit where you kind of have to kind of expand your mind a bit. So we're saying if you give me a morphism in mesh with this signature, it goes from X to P of Y, then by definition in the Kleisli category, that's a morphism from X to Y, just Y without the P. So that at this stage is a definition. Okay, so that probably means almost nothing to a lot of you at this point, but we'll take that as a given for now. So now we have to define composition. Okay, so if you give me, suppose we also have Q from Y to Z in the Kleisli category, we have to be able to define Q after P, which goes from X to Z in the Kleisli category. So let's think a bit about the signatures here. So if Q goes from Y to Z in the Kleisli category, by definition, that means in mesh, Q is a measurable function that maps Y's to P of Z's. And the signature we're looking for is a morphism that goes from X and it goes to P of Z's in mesh. And this is not immediately obvious because things don't quite line up, right? So what we have at our disposal is we have P, we have P and we have Q, right? But if you check their signatures, they don't quite line up because P goes from X to P of Y, whereas Q takes as input Y, right? We want to do Q after P, but Q needs a Y, but P gives us a P of Y. So it's not immediately obvious how we're going to do this composition. But let's see what we can do. So what we know for sure is we need to go from X to P of Z. So we need to start with an X. And if you give me an X, there's currently only one thing we can do with the X, and that's apply P. So that's certainly going to be the first thing we do. We're going to apply P, and that gives us a P of Y in mesh. And now we run into the problem I just said. Because what can we do with a P of Y? With what's written on the page, nothing, because Q requires a Y, not a P of Y. But don't forget that curly P is a functor. So if we go back to what we saw before, functors, what they do is they lift morphisms. So it's written with F here, but replace all the F's, the capital F's with P. Because if we consider now P of Q, curly P of Q goes from P of Y to P of Z. Right, remember Q went from Y to P of Z. And if you apply the functor to a morphism, it lifts it to P of the input and the output. So now if we apply P of Q, this is going to give us a P of Z. But what we actually want is not a P of Z, but a P of Z. But remember what we just said about the monad is that the monad gives us a way to transform kind of generalized elements down to generalized elements. So if we now apply M of Z, this will squish down P of Z and just give us a P of Z. And you see now this composition of M of MZ after PQ after P has the right signature. It goes from X all the way to P of Z. And so this basically defines Q after P in the Kleisli category. Okay, so that all seems very, very abstract and horrible. But let me now try and convince you that actually this is something, if you're doing research in probability and statistics and machine learning, this is actually something you already know and love. So let's think for a moment. So what are the morphisms in this Kleisli category? Right, so by definition, P goes from X to Y in this Kleisli category, if and only if P goes from X to P of Y in mesh. So in other words, P takes as input a point X and it spits out a probability measure on Y. And so if I wanted to use more suggestive notation, I could have written this as Px, dy. Because what we have is literally an indexed family of probability measures indexed by X. And in fact, these morphisms are precisely Markov kernels. So for those who need a reminder, remember, what is the definition of a Markov kernel? So a Markov kernel is by definition a mapping XA to P of XA, such that if you consider P of X dots, this is a probability measure on Y. But there's an extra condition that says if you look at the mapping X goes to P of XA, where A is fixed, this has to be measurable. But actually, when we consider these kernels in the Kleisli category, the second measurability condition is automatically satisfied because of the way we define the sigma algebra on the probability spaces, space of probability measures. So that's one of the reasons why this choice of sigma algebra was really important. Even though at the time it was just a kind of technicality, that choice of sigma algebra actually leads to the morphisms of our Kleisli category precisely being Markov kernels in the traditional sense. You know, I learned this definition from Mine and Tweedy. It's exactly that definition. And so what is this composition that we've just defined? So now that we know that these kernels are actually, the morphisms are actually Markov kernels, what is kind of Q after P? And we'll write it in our familiar notation. So it goes from X to Z. So we just write it as X dz. So what is this composition? So the first thing we just did a P. So in other words, it's P X dy. The second part is we applied PQ. So we applied the push forward of the kernel Q. And so in other words, what that kind of means is we basically draw the Y, well, this Y that random Y we have from P, and consider its law on Y, and then do Q, which gives us a Z. And then we applied this MZ, which basically means we kind of take the average, or we take the expectation of that kind of intermediate law. So in other words, we then integrate this over that intermediate law, which is over the space Y. And so, we do that integration. And so this exactly recovers a Chapman-Kolmogorov. So again, so for those of you who have background in applied probability and statistics, machine learning, this composition of kernels is something we use, at least for me, on a day-to-day basis. But what I've shown you now is that it actually arises really organically from this very general construction within category theory of this Kleisli category applied to a particular monad, which was the Geary monad. And so in terms of technically spelling out this category, there are other things that we need to define. I won't do all of them. But for example, for this to be a category, we also need to have identity morphisms. So we need to have some identity on X, which goes from X to X in the Kleisli category. But remember, by definition, that means you go from X to P of X in mesh. And there is, of course, a canonical way to do this, because we kind of need an identity kernel. Well, of course, then the natural thing to do is, given an X, simply to map it to the Dirac delta mass at that point. And indeed, this is the identity morphism in the Kleisli category. And in fact, because this Kleisli category is so useful, the name that people typically call it is stock, short for stochastic. And of course, to fully prove that this is a category, we have to check things like associativity, and we have to prove rigorously that these are the identities. So those are the parts of the monad I didn't tell you about. So for example, this identity definition I've given here is also canonical in the sense that it works for any underlying space X. And so it actually also defines what's known as a natural transformation. And on top of this identity and this M we define, there are also these so-called monad laws, somehow coherence conditions that have to hold. But for this particular, for the Geary monad, of course, they do hold. And so it does define a bona fide category. In fact, actually, maybe I will, I see I'm coming to the end of my time. Maybe I'll just say one more thing about this, and then I'll go back to the slides for some kind of concluding remarks, and then we'll end the formal presentation for today. So I told you very roughly what a monad was. So a monad, technically speaking, is a triple. So it's this functor, which we had is P, is this mapping M, and also we need this identity mapping, and people often use the letter eta. And on top of that, you need these monad laws as well. And in fact, so I'll refer you to Paolo's lecture notes for the precise, what exactly are the monad laws. But if you kind of instantiate those monad laws in this particular category, actually one of the monad laws is the very heart of Monte Carlo. So let me just describe that for you now. So if you give me a probability measure just on any space, so pi is a probability measure on P of X, on X, there are two ways in which you could embed this probability measure into P of X. So one of the ways you could do it is you could take pi and consider a delta Dirac mass at pi. So this is a way of going from P of X to P of X. But there's another way you could do it. So again, if you give me a pi, what I could consider is, how about you just draw X from pi? Pi is a probability measure, so we can draw an X from it. And we could consider a delta Dirac mass at this point X, where X is drawn from pi. And we can just consider the law of this construction. So again, this takes P of X and it puts it into P of X. Because you see, it's a measure on measures. This delta X is a random measure because the X was random, X was drawn from pi. So this is a random Dirac mass. So in the first construction, we had a deterministic delta mass at pi. In the second case, we have a random Dirac mass whose random location is precisely drawn from pi. And so given this element of P of X, remember, we can always apply the transformation M of X to collapse it down to just P of X, which corresponds to kind of averaging over the law of the random measure, if you like. And the monad laws basically say if you do that in these two cases, so this goes down to P of X, this has to be the identity. And in fact, well, that's true in both cases because, well, in the first case, it's just a deterministic mass. So if you average over that, you just get pi. In the second case, it's basically say if you average over the random X, it is the same as just integrating with respect to pi. And this is precisely Monte Carlo. Because the whole idea of Monte Carlo is to say, well, we have this measure mu that we want to sample from. But we can't do it directly because it's high dimension, it's complicated, whatever. So what we're going to do instead is we're going to attempt to get samples of X from pi, and then we're going to average over those samples. And the strong law of large numbers, whatever you want to use, that is exactly the same as pi, is the identity. So that monad law is exactly, well, it is basically Monte Carlo. Okay, so that basically is probably all I want to say in terms of the maths. Let me go back to my slides now and just give some concluding remarks. If I actually see a hand, Sam, did you want to say something? Or is that an accidental hand? Okay, I'll keep going. Yeah, so just to summarize, what did we talk about today? So today I very quickly introduced these basic concepts of category theory, so categories, functors, and monads, very roughly. We saw this key example. So this category mesh and this Geary monad P. And I didn't give you all the details, but roughly. And we saw that stock, which was the collection of Markov kernels in measurable spaces, has this natural compositional structure. Composition is Chapman-Kolmogorov. That arises, in fact, as the Kleisli category of this Geary monad. So this Kleisli category is a very general construction that we happen to instantiate in this specific case of the Geary monad. So next time, we're going to take this one step further, because in fact, stock is the prime example of a Markov category. So, today's presentation was quite heavy in terms of measure theory because we were working with mesh and the Geary functor. Next time, we're going to get some of the payoff, because now that we've seen stock has this natural compositional structure, the idea of a Markov category is basically to abstract out that compositional structure of stock, kind of independent of its measure theoretic foundations, and give us a way to reason just in terms of that high-level abstracted algebraic structure. And that will give us access to this really cool tool known as string diagrams, which I alluded to recently. And I will also give you the details of that proof I flashed up earlier, which is this proof of reversibility of Metropolis Hastings just using string diagrams. And so I think that is a good place for me to stop. So let me stop the recording now.